Okay, continues from this slide, we can find out the amount of reflected wave, that is the V minus signal, in terms of the reflection coefficient. So according to this equation, you see that V minus can be expressed as the product of the V plus, the incident signal, times the reflection coefficient gamma. And the reflection coefficient, as you can see, is determined by the impedance on the transmission line and the impedance of the load, which is resistive in this case, so it's labeled as RL. So let's recheck the reflection coefficient, see what happens with these things. If say if RL equals to Z sub 0, what happens? If the termination resistance is the same as the characteristic impedance, the reflection coefficient becomes what? Becomes 0. So what is significance? It tells that all the incident power, all the incident signal is absorbed by the termination, providing that you have a so-called match termination. That is, RL equals to Z sub 0. If there is no difference in your load resistance and your characteristic impedance, well, then all the energy goes into the load and nothing comes back. The reflection coefficient is 0, okay, and things becomes much easier. And what happens if the load RL does not equal to Z sub 0? So let me put two extreme cases first. How about your termination is shorted? You have a short circuit at the termination. So for short circuit, what is the RL value? It's 0, right? So if RL equals to 0, what is the reflection coefficient? It's -1. So what does that mean? That V minus is this has the same magnitude as V plus, but it has a negative sign. If the reflection coefficient gamma is -1, that means all the incident power, all the incident signal is reflected. Well, because a short circuit does not absorb any energy. Okay? A short circuit does not absorb any incident energy. All the incident energy gets reflected back because of the short circuit property. And the signal, the polarity of the signal is inverted. So the voltage is inverted as minus, the V plus is inverted as minus V plus. Okay? Another extreme case is if your termination is an open circuit. So what is the impedance of the open circuit? Of an open circuit? It's infinity, right? 无限大嘛, huh? So if the termination is an open circuit, then what is the reflection coefficient gamma become? RL becomes infinity minus Z sub 0 divided by infinity plus Z sub 0, then it's 1. Mostly because you have infinity over infinity, right? So if you have an open circuit, the reflection coefficient is what? Is 1, which also suggests all the incident power is reflected. All the incident signal is reflected with its polarity, the same as the incident power. Okay, so short circuit, open circuit do not absorb energy. All the incident energy gets reflected back, but the reflection coefficient has a sign difference. Okay, for open circuit, the reflection coefficient is +1, and for short circuit, the reflection coefficient is -1. And any resistive load, any resistive termination in between, you will end up with a real reflection coefficient. Let me emphasize this. The reflection coefficient with resistive load is a real value, real number. On the other hand, if your transmission line is terminated with an inductor or a capacitor or a combination of reactive components and resistive components, then your reflection coefficient is a complex number. Okay? But so far, we are dealing with the simple cases. Providing that the termination is resistive, then the reflection coefficient is a real number. And it's a real number between 1 and -1. OK？ 所以再重述一下了哈。我们现在看到的是电阻性的负载，所以它的反射系数都是纯实数。而这个纯实数从我们刚刚讨论里头，你可以看到它是介于1到-1之间假如是开路的话是1嘛，短路的话是-1但这件事情在以后会比较麻烦一点。假如你的负载是电抗性的负载，也就是说它包含电容或者是电感的话，那么你的反射系数就会变成是 complex number， 会变成负数。OK？ 好。Alright, so because of the impedance mismatch at the right end, it will set up a V minus I minus signal going from right to left. And eventually, after another time, that another L over VP and another propagation time delay, the V minus I minus signal will reach to the left end. Which from the left end's perspective, the time delay is 2 times L over VP because the signal goes to the right and comes back. So you have a 2, factor of 2 to describe the round trip propagation delay. So you will set up another refractive signal labeled as V minus plus and I minus plus, providing that there is another impedance mismatch between the characteristic impedance of the transmission line and the internal resistance of the generator. So if RG does not equal to Z sub 0, it will set up another reflective signal that is the V minus plus, I minus plus. All right? If RG equals to Z sub 0, then the RG resistance will absorb all the incoming energy, and there will be no other reflected signal. All right. And how to calculate the signal V minus plus and I minus plus? Well, it's simple. You just write up the boundary condition again. That is, the total voltage over the total current should be the same ratio of RG. And considering that at the left end, you have another voltage jump at the battery, V sub 0. So the equation, the Kirchhoff KVL equation at this point, at this place, at this instant, should be written in as equation 6.39a. Right? So that's a KVL equation. But anyway, you can simplify the previous equation using the representation as I plus equals to V plus over Z sub 0, I minus equals to V minus over Z sub 0, and so on and so forth. And here, you will have another reflection coefficient. You have another, you can determine another reflection coefficient. This time you are looking from right to left. You are looking from this side with RG and VO. Okay, so looking this side. So on the right hand side you have Z sub 0. On the left hand side you have RG. So the reflection coefficient seen at this position and in this direction, gamma equals to 先写谁？先写看过去的 Rg 减自己这边的 Z0 Rg 加 Z0， 好不好？有人会把它写一个伽马 G， 或那边写个伽马 L， 把左右两边分开来，好，定义清楚一点 ，OK？ 所以也就是说 V 负的讯号跟 V 负正的讯号，因为 V 负正的讯号是来自于 V 负是讯号打到那个左边的边界所产生的，所以它们两个之间，也就是 V 负正 over V 负会是这一个左边的反射系数，讯号源端的反射系数，所以记好那个分子的部分相减的顺序，所以左边的反射系数是 Rg 减去 Z0 除上 Rg 加 Z0 ，OK？ So this slide shows you some different cases that I has already mentioned. If the termination is short circuit, then you will have the so-called total reflection. All the incident power get reflected, and the reflection coefficient is -1. The second case is you have an open circuit, RL equals to infinity. Then you also have total reflection. And on the other hand, the reflection coefficient is +1, positive 1, 正一. And the third case is the so-called matching mode. That is the termination RL equals to the characteristic impedance Z sub 0. So the reflection coefficient equals to 0, which means that all the incident energy, all the incident signal is absorbed by the termination resistor, and nothing gets reflected. So the reflection coefficient is 0. So you have something else. Well, if you have a load resistance RL that is smaller than Z sub 0, a purely real RL that is smaller than Z sub 0, you will get a negative reflection coefficient. On the other hand, if the RL is larger than Z sub 0, then you will get a positive reflection coefficient. 有没有观察到我刚刚讲的事情？这是三个极端的 case 啦，所以假如说第四个 case 的话，对于纯实数的负载，假如说你那 RL 值比 Z0 值小的话，它是介于第一个 case 到第三个 case 之间，所以它会是一个负的实数啊。那反过来讲，你的 RL 值大于 Z0， 但是小于无限大的话，你就会得到一个介于0到1的正实数的反射系数。OK， 好，那这边是相对简单的情形，这样也就是说你的负载是一个纯电阻的负载，那么你得到的反射系数是纯实数啊。但反过来讲，你是一个电抗性的负载的话，就会有 complex number 的反射系数。好，那接下来我们看6之1。请你要打起精神，好不好？为什么要打起精神？因为期中考一定会考，好不好？考这个最简单的啊，不会很难啊，对不对？所以你只要回家有练习，一定写得出来啊。那我就可以分做7、8个小题嘛，所以这一题大概价值30分啊，每年都有啊，OK， 你去看一下考古题啊，这一题一定都有，好不好？So let's look at example 6.1. We will introduce the technique so-called the Bouncing diagram technique for time domain analysis of a transmission line system, which is kind of the most fundamental technique that you can use to analyze a transmission line circuit in the time domain. And as we already mentioned that the length of the transmission line can be characterized by its propagation delay. So here you have a quantity, say, capital T. Capital T equals to the length divided by the velocity of propagation. So for this circuit, we are assuming that the length of the transmission line is 1 microsecond. The time delay is 1 microsecond, which is around in the order of about 200 to 300 meters, depending on the velocity of propagation on this transmission line. So 1 microsecond is equals to 300 meter in free space propagation. And in transmission lines such as coaxial cable or microstream line, the velocity of propagation is about 2 times 10 to the 8th. So it's about 66% of velocity of light in free space. So the time delay is in the order of 1 microsecond, is in the order of 200 to 300 meter. Okay? And here, as the figure suggests, the characteristic impedance of the transmission line is what? Is 60 ohm. The termination is 120 ohm, and the internal resistance of the generator side is 40 ohm. And the generator, which is a DC source, provides 100 volt. So, come on, please write up. Please find out the reflection coefficient at the left end and at the right end. What is RL? Gamma L, sorry. Gamma L. What is the gamma G? 来，动动脑，好不好？这边是多少？120加60分之120减60，还是60减120？看过去的减自己这边的，好不好？所以是多少？刚好等于多少？1/3还是负1/3？1/3嘛，120减60嘛，看过去的减自己的。好，另外一边呢？算出来没？-1/5嘛，40减60除上40加60嘛，对不对？好，所以第一件事先把左右两边的反射系数算出来，可以吗？ And what is the time delay? It's 1 microsecond, right? So, okay, here is the. So on the top is the calculation of the first signal, V plus signal. V plus signal is what? Can be calculated by what? By the source voltage times right? 就电压分压公式了嘛okay. So the V plus signal can be found at 60 volts, while the voltage source is 100 volts, right? And based on the relationship of characteristic impedance, I plus equals to V plus divided by Z sub 0, what is the current? I plus current, 1 amp, right? Because Z sub 0 is 60 ohm. The reflection coefficient at the termination, 你写作伽马好吧，你就照课本吧，伽马，它把这边叫做 recessive low 左边叫做 source 精彩了，1/3跟-1/5那我刚刚跟你讲的，我们就算电压的就好。那这边把那个电流的反射系数也算出来，但不要理它，好不好？其实电压反射系数跟电流反射系数是差一个负号而已啦，我们就记电压反射系数比较单纯不要弄那么复杂。好了，下一件事情preparing the bouncing diagram. So we draw a sketch like this. So you have a horizontal axis and vertical axis. Horizontal axis indicates the location, indicates the position. So to the left is Z equal to 0. To the right is Z equal to L. So the horizontal line suggests your transmission line position. And the vertical line suggests the time progress. The change in the time, So as you can see here, indicates with arrowhead, labeled as T, going down. So the lower it goes, which means suggests the time progresses. 所以横轴是位置， 横轴是位置，纵轴是时序啊，时间上面的顺序。所以我们接下来要去做的事情叫做准备这一个 bouncing diagram 啊，我们用 bouncing diagram 这个技巧来去进行传输线电路的时域分析啊 ，junction analysis 站态分析。Alright, so the first thing is preparing the bouncing diagram with this configuration. So for your convenience, please do label the reflection coefficient on the right hand and the left hand. So to the right, the reflection coefficient is 1/3. To the left is minus 1/5. The horizontal axis represents the position, while the vertical axis represents the time progress. So the first thing is draw the V plus signal, which is a tilted line going from left to right. So as the figure suggests, you know that at t equal to 0, as the time progresses, the signal goes from the V plus signal goes from left to right. And at the time instant of 1 microsecond, which is the propagation delay of this section of transmission line, the V plus signal reach to the right end. And we would like to know what is the V minus signal. Using the calculated reflection coefficient at the low and at the source, because the reflection coefficient is 1/3. So the V minus signal is what? It's 20 volt, right? It's 20 volt, 60 times 1/3. However, if you stand at this end, what you observe is at the time instant of 1 microsecond, the voltage on the left hand jump from 0 to 80. Why? Because you observe V plus and V minus signal at the same time. So 80 volt is the summation of 60 and 20, right? So it jumped from 0 to 80. And the signal goes to the left is the V minus signal, which equals to 20 volt. And if you stand at this point, at the left hand, beginning from t greater than 0, here you observe 60 volt, right? Because from 0 to 2 microsecond, you only have V plus signal. And how about this place? At this place, you will observe V plus, V minus, and V minus plus at the same time. So what is the V minus plus signal? V minus plus equals to V minus, which is 20 times gamma S, which is minus 1/5. That will be minus 4. Okay? So at this end, after 2 microseconds, you will observe 60, 20, and minus 4 at the same time. So the total voltage at the left end becomes what? It becomes 76 beyond 2 microseconds. Right? So because the V minus plus signal is minus 4 volt. So the total voltage at this end is 76. And this process can be continuous infinitely, right? So at this moment, that is time equals to 3 microseconds, you will observe V plus, V minus, V minus plus, and V minus plus minus, which is minus 4 times 1/3, that is minus 4/3. So the total voltage here is 224/3. Well, I bet that you are starting get tired, right? But this process can be carried on infinitely, all right? You can carry on so on and so forth. So this is the V minus plus minus signal, and here is the V minus plus minus plus signal, and here is the V minus plus minus plus minus signal. Have you noticed that the higher order terms. The thing goes bouncing back and forth continuously. However, the magnitude of higher order terms are what? Are getting smaller and smaller. Why? Because the reflection coefficient on the right is 1 over 3. The correction coefficient on the left is minus 1 over 5, which are both smaller than 1 in terms of magnitude. And we know that higher order terms are product of previous term times the reflection coefficient. And as long as the reflection coefficient is something smaller than 1 in terms of magnitude, the higher order term will become smaller and smaller. You see, here is only about 1/10 of a volt, while the fundamental one, the lower order one, are 60 volt, 20 volt. Here is just 1 volt. So eventually, what happens on this transmission line? Eventually, the voltage signal, the total voltage signal, the total current signal on the transmission line will reach the so-called steady state, 稳态。它上面的电压电流讯号虽然有无限多的高阶项、衍生项会跑出来，但是最终会越来越小。我们可以说它收敛了。当它收敛了之后，你在传输线上所观察到的电压电流就会进入到所谓的稳态。这一段叫做暂态 （transient）。那这一段以后，比如说讯号大小 converge 之后，收敛了之后，你进入到的是 steady state 稳态，可以吗？好。Alright, so if you observe in this case, we observe the total voltage at a specific position at a different time. So you see the vertical axis is the total voltage at z equal to 0. The horizontal axis is the time progress from 0 microsecond, 2 microsecond, 4 microsecond, 6 microsecond. And at the beginning, you have 60 volt because you only observe V plus signal. Then it becomes 76, and it becomes a little bit less than that, and goes up a little bit. So what is the voltage at the steady state? 猜猜看，稳态电压是多少？有没有人猜到的？这个是左边端了哈，这个呢蓝色线的呢是中间那个位置，所以中间那个位置你看它 0.5 的时候才跳起来嘛？为什么？因为开关关上的时候，它需要 0.5 个 microsecond 讯号才会到达这边嘛，所以它一开始的时候看到的是 V plus， 所以是60。在 1.5 个 microsecond 的时候，同时看到 V plus 跟 V minus， 所以是80。而在 2.5 的时候看到 V plus、V minus、V minus plus， 所以是76。然后这样一路看下去，你会发现它的位准，这个位准跟这个位准是不是应该差不多？好，那这个是横轴了哈。So in this line you can observe from another perspective. So the horizontal axis is z-axis, is the location, while the vertical axis is the voltage across the transmission line. So say at a specific time instance, say at 2.5 microsecond, that is the red line drawn here. If you draw this line over here and you observe the voltage difference at the different positions, you found that to the right is 80 volts, to the left is 78 volts. Okay? So there is some difference, but the difference shall become smaller and smaller as the time progresses. So eventually, you can observe the steady state on the transmission line using the bouncing back, using the bouncing diagram technique. So if you collect enough turn, you found that the total voltage on the transmission line shall converge to what? Well, I bet you can guess from this number. 75 volt. How about the current? Total current on the transmission line will converge to what? 0.625 0.625嘛，0.625安培，总电流0.625安培，总电压的75欧姆。还记不记得我们这个电路它的左右组成是多少？我们跟各位讲过，刚刚今天一开始上课的时候就讲说，对于电路的时域分析，一开始站态分析的时候，你会看到传输线的效益，但是假如你观察的时间够久的话，传输线的效应就不见了。所以这边是几伏？我忘记了，多少？100。然后这个是40嘛，传输线本身是60伏，60欧姆一个 microsecond。但这边是120伏，120欧姆 ，OK。所以，假如进入到稳态，进入到 steady state， 这个拿掉，直接连过去。所以它上面的电压，这个地方电压多少？75嘛，对不对？这个地方电流呢？100除以160，有没有？好，所以但是那个广告是给你一个 detail 的分析啊。我们看到有一堆项在那边弹来弹去，弹来弹去，但谈到最后的结果是什么？谈到最后的结果进入到稳态的时候，其实传输线效应就不见了，好不好？所以记得考试的时候，最后问你稳态电压、稳态电流是多少，你可以直接把传输线拿掉，直接算，好不好？这样子免得你传输线那边写错了，你后面也跟着错，好不好？好。Okay, so we can. So as the time progresses, you will reach the so-called steady state for sufficient observation time. So here in this slide, you see that at z equal to 0, z equal to L, that's to the left hand, that is to the right hand, that is in the middle. As the time progresses, the voltage converges to 75 volt. And from the perspective of currents on the transmission line, it is equal to 0, z equal to L, z equal in the middle, L over 2. The currents will eventually, even though they are quite different at the beginning, but as the time progresses, they will converge to 0.625 amp eventually. So as long as you observe for a sufficiently long time, the currents and voltage will converge to the same value on the transmission line for the case of a DC voltage source. OK? 当然，这个结果它是限于使用 DC voltage source。我们等一下，或者说我们接下来会看一些不同的 source， 像是 sinusoidal source 或者是 impulse source 脉冲的讯号源，或者是正弦波的那个讯号源，那结果会有些不一样但这边的话是定电压源了所以定电压源的结果看起来就相对单纯OK， and this is the result concluding from bouncing diagram. Okay, and if you are good enough in terms of math, in fact, you can write out the so-called analytical solution using mathematical approach. So here we try to write out the steady state voltage, steady state current, based on the concept of reflection coefficient and the concept of infinite series. All right. So V plus SS is what? SS represents steady state. V plus is the collection of all the positive going voltage term. So you have V plus, V minus plus, V minus plus minus plus, and then a more higher order term. All right. So the V plus term is 60. The V minus plus term is minus 4. And the next term that's going from left to right is 4 over 15. The other one is another number. But if you observe this, you can say that it's a 等比级数啊，对不对 Okay, so it's a series with a ratio of -1/15. So this is the zeroth order of 1 -1/15. This is the first order of -1/15. This is the square of -1/15. So the next one is the cube of -1/15. So you can write out the solution, and the analytical solution of this infinite series that will be 56.25. That is the steady state voltage going from left to right. The voltage value is actually 56. You can do the same for V minus SS. That is the steady state voltage, all the reverse going or backward going voltage term. So that will be V minus plus minus, V minus plus minus plus minus. So again, the difference between each term is -1/15. So you have another infinite series beginning from 60 with this, the same one. So the number is 18.75. If you add up the two terms, it becomes what? Becomes 67. All right? And you can write up the corresponding current term, steady state current term. So I plus SAS is 0.9375 amp. And I minus SS is minus 0.35. You notice that the ratio of steady state voltage and currents for both forward-going and backward-going components remains as a 60 times ratio, which is the same as the characteristic impedance of the transmission line. So all the forward-going part and all the reverse-going part, the ratio of characteristic impedance shall be kept as 60 times, as 60. However, if you add up the forward-going and reverse-going part together, the total voltage is 75, the total current is 0.625, which is not a ratio of 60. All right, so it's not the total voltage which comprises forward-going and reverse-going components do not have to obey the characteristic impedance ratio. Nevertheless, for all the forward-going and all the reverse-going components, they should abide the voltage over current ratio, which is the same as the characteristic impedance. All right, so here is a simplified illustration of the transmission line circuit, providing that you observe the signal for a sufficiently long time. That is the steady state circuit. So as you can see here, the transmission line component is eliminated in the steady state. And the result is the same as lump circuit analysis result. You simply ignore the transmission line, and you can directly find the steady state voltage and steady state current using lump circuit analysis result. 用传统的电路学分析就可以找到稳态的结果。那个时候在稳态分析的时候，其实传输线效应是看不出来的，就像这边所说的。The series inductance and shunt capacitance of the distributed circuit of the transmission line circuits model does not come into play for steady state analysis. All right? At the steady state, the shunt capacitance becomes open circuit. The series inductance becomes short circuit. 有没有？我们在电路学分析电感跟电容的时候，有没有一个口诀？当时间越来越大的时候，当时间随着时间增加，电感会变成什么？短路嘛。电容会变成什么？开路。电容会变电容会变开路，电感会变短路。所以原本的那一个传输线模型， 电感短路，电容开路，电感短路，电容开路啊就不见了，对不对？好，我们在电路学里头讲的不是吗？时间足够久的话，电容开路，电感短路嘛。啊，所以时间足够久的话，重出现的效应就看不到了。所以你可以直接用电路学的分析计算 steady state 的结果，对不对？好，所以这一页的话呢，是比对那个 time domain 上的分析跟那个 spatial domain 上的分析哈，所以这边横着看的话，其实跟这边是可以对比得上的哈。左边这个是 2.5 个 microsecond 啊，这一条是 2.5 个 microsecond 的结果哈。然后这个是 current 的这个部分了哈，这是1/3个 microsecond 的时候。所以1/3个 microsecond 的时候，你有 I 正的讯号，还有一部分的 I 负讯号 ，I 负讯号会跑1/3的距离哈，到2/3L 的这个位置，所以这个是它的电流的那个电流的分布啊，在特定时间点，在不同位置上面的电流分布，总电流是1哈，但是这边的总电流，因为这边只有看到 I 正，这边有看到 I 正跟同时看到 I 正跟 I 负，所以它会变成是2/3 ，OK。So, in example 6.1, we introduce the bouncing diagram technique for a constant voltage source. The technique can also be applied if the voltage source is a pulse. So the bouncing diagram is also applicable for pulse source, which means that the signal, the source signal, is not necessarily a constant voltage source. It can be a step signal. Step signal source. It can be regarded as a superposition of two step functions. So this step source. 也就是说，你看一下左边这是等于这项，也就是在 t 等于0的时候起来到 v0， 但到 t 等于 t0的时候又下去，所以它只给你开了一小段时间，也就是 t0的这段时间。它可以被视为是2个 step function 的加总，一个是在 t 等于0的时候上去，这个是在 t 等于 t0的时候下去，所以这2个相加会得到这个结果。这个东西跟这个东西差别在哪里？右边的这个 step function， 也就是在 t 等于0的时候打开给你 V0 的那个电压。它代表的是你的 voltage source， 你那个电池持续给你能量，在这个传输线上。所以只要你观察的时间够久，它的那个给的能量是一直推进来的。也就是说，对于这个传输线路这一个 function， 我是没有这一个这一个部分 state function 呢，它是一直提供能量的。但是这一个呢？这个也提供能量，但是只有在0到 t0之间，对不对？所以它提供的能量是有限的。也就是说，观察的时间够久，在这个传输线上会发生什么事？当然了，一开始的时候，当你的讯号源打开的时候，这一个传输线上会有能量。但是久了之后会发生什么事？能量会耗损啊！耗损在哪里？耗损在哪里？在我们目前所学的传输线路里头，哪些东西会吃能量？右边的负载电阻跟左边的电阻嘛，对不对？这个2个电阻会吃能量所以只要观察的时间够久，这2个左边右边有电阻在的话，讯号是会被吃掉的所以这边的话，我们看的是 example 6.2 shows another example for transmission for the analysis of bouncing diagram. On the other hand, the signal source applied is a voltage source that are only activated between t equals to 0 and t equals to 1 microsecond. In other words, the voltage source only provides a limited amount of energy onto the transmission line. So let's see what happens on this transmission line. The calculation of the V plus V minus signal is the same as before. So beginning from t equals to 0, you observe 60 volt foregoing voltage signal going from left to right. However, at a time equals to 1 microsecond, the voltage source is shut down. So it no longer provides the V plus signal. All right. However, the V plus signals that appear between 0 and 1 microsecond reach to the Y from 1 to 2 microsecond. It shall produce a reflecting signal of 20 volt, the V minus signal going from right to left, and it will produce the following V minus plus signal as minus 4 volt. And it will produce another signal of minus 4 over 3, and so on and so forth. However, we notice that the voltage signal becomes smaller and smaller. And the total energy on the transmission line system is what, on the transmission circuit is what? Is also getting smaller. Also becomes smaller and smaller. Why? Because the limited energy provided by the voltage source from 0 to 1 microsecond are absorbed. Absorbed at the right end, at the left end, by the load resistor RL and by the source resistor RS. So you can see here are the drawing for voltage observation as the time progresses to the left, to the right, and in the middle. At the beginning, you observe strong voltage signal because the voltage source provides the signal between 0 and 1 microsecond. However, as the input signal, as the input energy, injected energy are absorbed by the termination resistor and the source resistor, the voltage signal observed on the transmission line becomes smaller and smaller. And what happens in the steady state? What happens in the steady state? Well, simple, there will be no signal because all the energies are dissipated on the terminated signal, terminated resistor and the source resistor, right? So eventually, the signal will be absorbed by the. So here is another perspective viewing the signal. Okay, so here is the result of a specific time instant t equals 2.25 microsecond. And at this time instant, the signal will, the leading edge of the signal will goes here. 注意啊，这个是在这张图显示的是在 2.25 microsecond 的时候。注意啊，因为刚刚那个讯号源它是从0到1开，它的持续时间是0到1，所以在 2.25 个 microsecond 的时候，你的那个讯号的前缘，也就是一开始在 t 等于0所产生的讯号，会在这个传输线路径上走多少趟？走2趟多一点点嘛，对不对？因为1趟是1个 microsecond 嘛，所以2趟是2个 microsecond。现在我们看的是 2.25 microsecond， 所以你一开始在 t 等于0的时候灌进来的那个60伏的讯号，在 2.25 microsecond 的时候，它会走到哪里？会走到回来1/4的地方。但是这个时候呢，这个讯号它从 V 正变成 V 负，然后变成 V 负正，所以它的大小只剩下-4伏。而这个0到1 microsecond 的这个打进来的讯号，它的尾端在传输线上走了多久？ 1.25 个 microsecond 嘛，对不对？前端走了，因为它持续了1个 microsecond， 前端走了2.25 个 microsecond， 那尾端呢 1.25 个 microsecond， 所以它走到哪里？走到过去再回来一点点，走到过去再回来1/4的地方。而这个时候呢，这一段呢，它是以 V 负的信号存在，所以它是20伏。所以前端已经变成-4伏了，后半段呢，前面的1/4是。前面的1/4是-4伏，后面的3/4是20伏，所以加起来变成这个样子。这边是16，这边是20，这边等于0。随着时间下去，它会越来越弱，越来越弱。OK， 因为被左右两边的 termination 吃掉了。 教完了，6点要教，下礼拜要教第4个作业哦。